So I'll start by an introduction to the trace gas analyzer platform with a brief look also at the LI-7000 technology and also the NDIR technology, non-dispersive infrared, that is also included in the 830, 850, which still make up part of Apollo's systems. We'll look at the platform in terms of specifications, general specifications that are common across 3 different analyzers that we manufacture. And also, then we'll move into the measurement principle. I'll just give a brief overview here, comparing mid-IR, NDIR, which is used in the 7000, 830, 850 instruments versus near-infrared optical feedback cavity-enhanced absorption spectroscopy. Also, then we'll look at the performance of that instrument, what that delivers, and give some model-specific specifications, again, focusing on CO2. So if you look at the LI-7000, this is a differential non-dispersive infrared NDIR gas analyzer. The CO2 and H2O measurements are based on the difference in absorption of infrared radiation passing through 2 sampling cells. So cell A is normally the reference cell that's used for a gas of known CO2 or H2O concentration. And then cell B, normally the sample cell, is used for a gas of unknown concentration. And you can see the schematic on the left here. The infrared radiation, in this case, is from a broadband lamp source. It's transmitted through both cell paths, and it's showing one path here, A or B, where it's then collected at the detector after passing through the sample or the reference cell. And it's H2O or CO2 is measured depending on which detector is selected. Now, we recently announced end of life of this instrument for several reasons, and that's effectively now being replaced, the 7000, by the LI-7815. But the same principle is used in the 830, 850 instruments with a single optical cell. So that's something that you will talk about in terms of how those are integrated within the Apollo systems. Looking at the trace gas analyzer platform, as I say, we've got 3 different units currently available. One of those is the high precision CO2, which is the LI-7815. They use combined patented technologies which balance performance and design. So you can see they're very much designed for portable outdoor use by our research customers. But using that optical feedback cavity enhanced absorption spectroscopy technique, we also get very high performance for laboratory-based applications, of which pCO2 measurements is one, but also atmospheric long-term background measurements where there are high demands on short-term precision, but also long-term stability and drift. And what we deliver in this package is performance in the field that's comparable with the same instruments if you were to use them in the laboratory. So a very rugged and hardy design that can be deployed in many different ways. The instrument is self-contained, and you can see it's powered by 2 hot swappable lithium-ion batteries when it's not connected to an AC power supply through this connection here. But in a laboratory setting, those batteries then become an uninterruptible power supply should there be interruptions in direct AC power, which could be very useful in certain situations. It is designed to be portable. It's 10.5 kilograms. You can see it's easily carried with a handle here. There's an onboard display. And you simply can connect to the instrument using either the wired Ethernet connection or fully functioning Wi-Fi capability. So you can log into the built-in server using a smartphone or tablet to get full access to control and data. So it's very, very simple to operate as a standalone unit with just an inlet and outlet gas connections, that Ethernet connection and power. There's very little more to do in terms of general use. It was designed for outdoor use by our customers doing applications like soil flux measurements. And typically they're operating in a very wide range of environments. And so it was designed to operate between -25°C right up to 45°C without any additional cooling or heating, which gives it great flexibility when being used in the field. As I mentioned, it's relatively lightweight, so it can be carried and installed in the field. In terms of the measurement, we're making one sample per second. It is making multiple measurements, but processing that to deliver one measurement per second. And we have standard flow rate of 280 SCCM with an optional lower flow rate, which is often taken up by our atmospheric users where they're using expensive calibration gases, for example. Unlike a lot of instruments of this type, the cavity volume is very, very small. So combining that with that high or reasonably high flow rate, you get excellent throughput and also gas response. So you're not basically diluting the sample in a large cell and waiting for that to then exchange over a long period of time. And key to this technology, much like other cavity-enhanced systems, is that we use or employ a optical path length of several kilometers, and that becomes important when we look at the laser source that we're using for these instruments. In the next slide. So laser absorption spectroscopy, this applies to basic TDL systems through to cavity-enhanced systems. Essentially, we're starting with a light source, in this case, near-IR laser, or in the case of the 7000 and 850, this is a broadband lamp. We have instant light of a given intensity passing through a sample, and if the wavelength of the light interacts with the molecules in the sample, then some of that light is absorbed, and that's then detected as a drop in intensity at the photodetector. The measured absorbance that we observe is proportional to the molar absorptivity coefficient of the gas in question, the path length of the cell, so this path length here, and also the analyte concentration, how much of the analyte is in our gas that we're measuring. To affect the absorbance that we measure, we can either change the path length or the analyte concentration. Now, changing concentration by pre-concentrating, if we're measuring very low concentrations of gas, isn't very practical because we need a pre-concentration trap or system, which adds complexity to the design. So really the only parameter we have to play with to improve that absorbance measurement is the path length of the cell. Now for the LI-7000 with a broadband light source operating in the mid-IR, that's not such a problem because the absorption intensity is very, very high. If we move to the laser-based systems operating with diode lasers in the near-IR, then we get a much weaker intensity of signal for any given molecule that we're looking at. And so, as I mentioned before, we need to greatly increase the path length that we use when we're using these near-IR sources. There are, however, great advantages when moving from broadband sources to laser-based sources. So on the left here, you can see the resolution or the spectral resolution of the broadband approach is just 16 centimeters to the -1, compared with 0.001 centimeters -1 for the laser-based system. So on the 7000 and 850, we're looking at very broad features here, overlapping features that we need to tease apart to calculate the concentration accurately. Whereas for the laser-based systems, we can zero in on individual transitions of the molecule. So we can find a line that is potentially, or as best we can, free from interference from other gases that we would expect to find in our gas sample, like water, for example, which is everywhere in the spectrum there. So we can minimize interferences and also just zero in on the gas of interest. I mentioned that we need to increase the path length, and the approach that we take to do this is by using a cavity-enhanced absorption spectroscopy technique. And we use one variation of this, which employs some optical feedback to improve the measured signal. Now, with the robust near-infrared diode laser, that's our source. These are lasers designed for telecoms industry. They're designed to run for many, many years without degradation, so they're ideal for spectroscopy. But as I mentioned, the intensity of the absorptions are low, so we need to greatly increase the path length. And we do that by trapping light in a high finesse cavity using mirrors with extremely high reflectivity. So only 100 ppm of light leaks through or transmits through that mirror when it hits the mirror. The majority of the light is reflected back and is trapped in that cavity. So you can see here, with our approach, we have our near infrared diode laser passing through mirror 1, hitting mirror 2, and then, as I mentioned, a small proportion of that light is then transmitted, such as 100 ppm on each pass. The majority of the light is reflected back and trapped in this V-shaped path between mirrors 1, 2, and 3. And so a path length which is, in practice, just a few centimeters. As I mentioned, the volume of this cell is just 6.4 centimeters. We get an effective optical path length of that instrument of several kilometers. So imagine many, many thousands of passes in that tiny, tiny cell. And that gives us the signal we need to make the calculations. And here is what we observe using the instrument. We look on the left here. To change the wavelength of the light coming from the laser, we essentially just change the current that we apply to the laser. And we sweep across wavelengths of interest where we know we would get an absorption feature from the gas in question. So you can see here on the top left, we've got a zero gas. We're not expecting any interaction, and that's exactly what we see. We pick up these signals at each resonant frequency within the cavity. And if we then sweep across a wavelength of interest where the light interacts with the molecule, we can see this absorption of light as it passes through that feature. And that can be converted to absorption spectrum to calculate concentration. On the right-hand side, we can see a full spectrum here. This is the LI-7810 measuring methane, CO2, and water vapor with a single laser. So they are tunable to a small degree where we can pick up multiple gases with a single laser. Typically one or two, in this case 3. And this is the full spectrum. We're taking many, many spectra per second, processing those to deliver that true 1 Hertz measurements of one measurement every second. In terms of performance, we'll focus on the 7815, as that's the gas of interest there is CO2. It gives you a wide concentration range using this technique, so 0 to 10,000 ppm, and it's a linear response across that range, so calibration is very simple. In terms of precision, we get very, very good short-term precision, 0.1 ppm in 1 second, 0.04 ppm in 5 seconds. One characteristic of this technique and the optical bench is that we get extremely good drift characteristics, a very, very low drift over a long period of time. And that's essential for atmospheric measurements or indeed field measurements where we don't want to be using expensive, cumbersome calibration bottles in our experiments where at all possible. So here you can see we have very low drift delivered by this platform, 0.2 ppm or less than 0.2 ppm in a 24-hour period. So just to summarize before I hand back to Yi to talk about the Apollo systems, we gave a very brief overview of LI-7000, including NDIR, and touched on the 830, 850 instruments that are still in service. And then we gave an introduction to the trace gas analyzer platform that will be replacing the 7000. So we gave some general platform specifications, an overview of the measurement principle, compared that with the NDIR approach used by the 7000 and 850. And then we looked at some model-specific specifications, focusing on that performance for high-precision CO2 delivered by the 7815. And with that, I'll hand back to Yi, who can talk about how these instruments are integrated with the Apollo systems. Thank you.
Thank you, Graham. Hello, I'm Yi from Apollo Scitech. First, a little bit about the company. Now we have been here in Delaware for 7 years. And before that, the company was in Georgia for 13 years. And we provide high quality scientific analyzers at affordable prices for the measurements of pCO2, CO2 parameters, including dissolved inorganic carbon analyzer, stable isotope of DIC, seawater total alkalinity titration system, underway pCO2 monitoring system, and a spectrophotometric pH analyzer. These CO2 parameters are used for biological activity researches in aquatic environments and for climate change related researches. So our users are mainly researchers all around the world. First, a little bit scientific background. Okay, I didn't get the pointer started. So the CO2 concentration in the atmosphere has been relatively steadily fluctuating between 190 ppm and 280 ppm in the past 2 million years, although this figure only goes back to 400,000 years. And see this inset, the concentration has been stable all the way down to 1760 when the Industrial Revolution started. And then the CO2 has dramatically increased to over 410 ppm today. And this is all due to anthropogenic activities. Well, we have the ocean to take up a lot of this CO2 that alleviates the CO2 level increase in the atmosphere. But this causes ocean acidification, which negatively impacts coral and the shellfish growth, as well as the health of the entire ecosystem. And when CO2 dissolves in water, it becomes carbonic acid in a series of reactions in which bicarbonate and carbonate ions form. Then there are 4 parameters to measure in the CO2 system, and we have instruments to measure each of them. And the parameters are partial pressure of CO2 dissolved in water, pH, dissolved inorganic carbon or DIC, and total alkalinity. Today, we'll just focus on these 2 that are realized by taking CO2 measurements. The pCO2 system measures the carbon dioxide that dissolves in the water sample by measuring the CO2 concentration in the air that's equilibrated with the water sample. And the DIC analyzer uses phosphoric acid to convert all the carbonate and bicarbonate to CO2, and then extracts everything with a carrier gas. In both cases, our equipment processes the water sample to extract the CO2 and send the gas sample to LI-COR analyzers to get the CO2 concentration readings. First, the DIC analyzer. What's shown here is our Model C6 with LI-7815 on the outside. And this model can also be equipped with a an LI-850, and I'll talk about that in a minute. With this model, we can provide a precision better than 0.1%, or about 2 micromoles per liter for a typical seawater with a DIC level around 2000 micromoles per liter. And what you see here is a multi-sampler. There's a 12-port valve here. 1 port is dedicated to standard, and 8 ports are for samples. The sample volume is between 1 and 4 mils for each repeat, and this number can be changed by the user. One advantage of this whole setup is that it only needs 1 standard solution. And the 3 different volumes of the same standard and 8 samples are fully automated. And each repeat takes about 3 to 4 minutes. This is the Model C5. It has the same case, but LI-850 is small enough to fit on the inside. This is a view from the side. So the 850 is right over there. With this model, it's more compact and it costs less. The precision-wise, we can provide 0.15%, or about 3 micromoles per liter for a typical seawater. And for freshwater samples with DIC level around 130 micromoles per liter, we can provide a precision better than 0.5%. This is a screenshot of the program. As I said just now, sample volume can be changed by the user, but we also give you the flexibility to change many other parameters so that you can fine-tune your instrument to better suit your samples. What's shown here is the wait period between each repeat, each sample. You can control the acid volumes, how fast you inject everything, and when you consider a repeat to be good enough to finish. Also, usually we do 3 repeats out of a maximum of 5. Again, you can change that if you only want 2 repeats that are close enough. And you can you can change the volume of the standard here, and you can choose whether you want a best fit line or broken lines when you deal with the standard curve, which I will talk in a minute. And that's the plot area. Earlier I said we use a carrier gas to extract all the CO2 from the water sample. So as the carrier gas flows through this, as the reaction between the phosphoric acid and the carbonate species occur, the carrier gas flows through the system. And we constantly measure the CO2 concentration in that carrier gas. So we get an initial baseline, this peak, and a final baseline. After we get this integration curve, we use the area underneath this curve as a measure of the total amount of carbon. So with that, we can use a smaller volume of the same standard in place of a second standard with a lower concentration. In this plot, we have 3 volumes at 0.8 mils, 1 mil, and 1.2 mils that represent 3 standards at 1600, 2000, and 2400 micromoles per liter. And with this standard curve, like I said just now, you can get a best fit line, which is also shown here with a very good R² value. Or if you want, you can use the broken line between 2 adjacent volumes to calculate the DIC of the standard. The DIC of the sample. So for the sake of simplicity, I'll refer to this as the standard curve. Then this is the data table in the software. We record sample ID, port assignment, volume of the sample, start time, and how many attempts there were for you to identify the sample. And these columns are parameters of the measurements. They also help us to monitor how well the instrument works. And this section would be the result. We report the integration area of each repeat, as well as the average of those 3 repeats that are close to each other. This column displays the DIC. We input 2000 as the concentration of the standard for this example. And these numbers were calculated for each sample based on its average area, as well as the standard curve generated by these 3 volumes, the average area, and the input DIC concentration. The status column is color-coded. Here you can see an example whether the repeat was halted by the user, was not so close to the other repeats, they were close so they were valid, or they failed to be close to each other, or they were just analyzed so we don't know the status because more repeats of the sample are still being tested. And the pending samples are in blue. Are in yellow. This screenshot was taken on a single sampler. So you'll see the port assignments will be different because everything has to go through the same, all the sample and standards have to go through the same port. Here's an example of calculating the calibrated DIC. This system with LI-7815 is very stable. So over time, it doesn't drift much. As we can see here, the area of the three volumes of the same standard changed only on the unit digit within about 2 hours. But if you want to correct for the drift, this example shows you how to assume that the area changes linearly with time and how to calculate a concurrent hypothetical standard curve for that sample. As you can see, the correction is very small. It's still within 0.1% as the precision we maintain. Here, I want to show you a video of the operation of the system. Turn that off. In the video, we have a single sampler. Again, all the standard and sample have to go through the same port. But the whole process is still automated. You just have to come in and change the sample. Okay, so now the underway pCO2 system. This system is used for underway pCO2 measurements aboard a ship. And water is continuously pumped into the equilibrators. Let me turn on the pointer. Into the equilibrators while the ship is sailing. And the water is sprayed into the equilibrator through a shower head to accelerate the gas exchange between the water sample and the air inside the equilibrator. Then the air is sent to LI-7815 for CO2 readings. The system also automatically measures the atmosphere and CO2 standard gases. I don't think you can see that in this picture clearly, but there's another equilibrator behind this one. The secondary equilibrator is designed to remove the bias introduced by the atmosphere. This whole design is based on an improved design from NOAA. The system has a rather small case and can't be custom built. Right now, it's compatible with LI-7815, and we're working on to connect it to a LI-850. The software now allows remote control and remote data access. A 99% response time between 2 and 3 minutes, which I'll talk more later. When I said this system can be custom built, that means these sensors are optional. Includes pH, dissolved oxygen, chlorophyll, and a GPS unit. Here are just more pictures from different angles to show you the components. This is SBE45, the selenothermograph. Water filters, there are two, one behind this one. The equilibrators, air filters, and the cooling module. This is the software. The system allows you to connect to 5 standard gases, but you don't have to use that many. Like in this example, if you leave it blank, the program will skip that port. This section is for UDP settings for the remote control. And this section again allows you to change many parameters in the measurement to better suit your project. We allow you to change how many measurements you want from each source, or how many times it repeats the air and seawater before it goes back to another group of standards. You can change how long you want to wait before each repeat is of the same source, or how long you want to wait before the new source gets measured. You can also change the flow rate, and when you consider a standard gas to be stable enough. This is the data table in the program. Here we report time in UTC, the coordinates from the GPS, and the readings from LI-7815, and all other probes that's not shown in this view. In this example, we have 2 standards, then air and seawater, according to the number I showed you in the previous slide. These are the plots. We give you 3 different plots. You can plot the historical data files here. You just have to select the data file first, which are named by the date and time it was started. Then you choose the different parameters to plot. So you can choose the same data file with different parameters like what I do here, or you can compare the same parameters from different files. This is the data table for export. The selected parameters are highlighted here, so it will be easier for you. And the file will be exported in a CSV file, comma separated value. Here's are the results for the response time test. It was done with a seawater and a tap water sample with different CO2 concentrations. Once we get a stable reading for the sample at around 300, we switch the water inlet to the other water body and see how fast the CO2 reading changes. And a 99% response time means the concentration changes for 99% of the difference between these 2 steady values. With that, we got a 99% response time between 2 and 3 minutes, and 95% response time around 2 minutes. A 90% response time would be between 1 and 2 minutes. That's all I have for the analyzers. This map shows where our current customers are located. As you can see, they are all around the world, in all over Americas, Europe, Middle East, and the Asia Pacific. We currently have 3 distributors in China, Italy, and Russia. So if you or your colleagues are from those countries, you need to contact them. Otherwise, I think most of you are from the US or other countries. In that case, you need to contact us directly. With that, I want to thank you for your attention, and I can take questions now.